So it's great pleasure to have Keita Nii. He's gonna from YITP Kyoto. He's gonna tell us about generalized Giveon-Kutasov duality. Please.
Okay, thank you very much. So first of all, I would like to thank the organizer for giving me this opportunity. Okay, today's title is Generalized Giveon-Kutasov duality. So today I'm going to talk about the duality. So in supersymmetric gauge theory, this is called a Seiberg duality or Seiberg-like duality. So in this seminar, duality always means a far infrared duality. So then we have two different UV theories. So UV theory A and UV theory B. And two theories are completely different. But going to the infrared, so by integrating out the massive mode, and only by keeping the massless mode, so these two theories become completely identical, and we can see that the two theories are in the same universality class. So in this talk, I'm often talking about this type of duality, infrared duality. Okay, so and this type of duality is a very powerful tool to study some strongly coupled or non-perturbative dynamics of the supersymmetric gauge theory. Okay. So Seiberg duality was first found in 4 dimensions. And let me briefly show you the most famous examples. So the electric theory A, is a 4-dimensional n equal to 1 SUN gauge theory with F flavors. Here, F flavors means the F fundamental chiral multiplet Q and F anti-fundamental chiral multiplet Q chilled. So this fundamental chiral multiplet corresponds to a quark, and the anti-fundamental chiral multiplet, roughly speaking, corresponds to anti-quark. This is nothing but a supersymmetrized QCD. And the dual description is given by a 4D n equal to 1 supersymmetric SU F minus n gauge theory with F dual flavors and a meson singlet. This meson is a gauge singlet field. And here F dual flavors again means F fundamental chiral multiplet, small q. This is a dual quark. And F anti-fundamental chiral multiplet, q chilled. This is the dual anti-quark. And on the magnetic side, we have a cubic type, Yukawa type superpotential between these meson and quark and anti-quark. So this is an infrared duality relating these theories with 4 supercharges. And there are F quark and anti-quark pairs. So then this is a vector-like theory. So today I'm going to consider this type of vector-like theory with F quarks and F anti-quarks. And this theory has 4 supercharges. So then this type of theory can show confinement and chiral symmetric breaking and supersymmetric breaking and so on. So if we consider more highly supersymmetric gauge theory, so in general, such a theory cannot have, for example, confinement. So in order to study some confinement phenomena, the theory should have 4 supercharges at most. Okay. Okay, so since this is an infrared duality, so massless modes must be identical on both sides. So since this is a supersymmetric theory, we have massless fermions as well as bosons. So in the infrared, there are also massless scalar modes. So along the flat direction of the scalar potential, which is called the moduli space, there are massless modes. So in order to see the validity of this duality, we need to understand the quantum flat direction. So quantum mechanically, this flat direction is modified. So then we have to understand the quantum structure of this flat direction. So as a simple test of the duality, we can see the matching of the massless scalar mode, which is called the moduli space. So on the electric side, we can define various gauge invariant composite. For example, QQ tilde is a mesonic operator, and this describes a moduli space. And we can also define a baryonic operator and anti-baryonic operator by using the epsilon tensor to construct a gauge invariant composite. So Q to the n and Q tilde to the nth order. So on the magnetic side, we have a gauge singlet meson field. So then you can simply identify M with QQ child. And on the magnetic side, you can also define the dual baryon and the dual anti-baryon by using dual quarks and dual anti-quarks. So then you can have a natural identification between these two baryon operators. And naively, there is a dual meson, small QQ child, on the dual side. So then you might consider that there is no counterpart on the electric side. However, this QQ2, the dual meson, is eliminated by the superpotential by considering the flat direction of this magnetic theory. So taking F-term condition, you can see that this dual meson is completely eliminated from the moduli space. Okay, in this way, you can see that the matching of the moduli space. So today I want to consider some 3D version of the Seiberg duality. So and this is known as a Gibeon-Kutasov duality, which has a Chern-Simons interaction in addition to a Yang-Mills interaction. So Chern-Simons action is like this. And the coefficient in front of this action is called the Chern-Simons level. So before going to the detail of this duality, so let me briefly explain the effects of some Chern-Simons gauge theory. So normally, we need a Higgs field to give a mass term to the gauge boson. However, 3D is very special, and in 3 dimensions, Chern-Simons term realizes a massive gauge boson. So okay, let us consider the Maxwell Chern-Simons theory. And if we write down the equation motion of this Maxwell Chern-Simons theory, its equation motion becomes like this. So now I'm writing the equation motion in terms of this F tilde. F tilde is defined from the gauge invariant field strength by contracting the indices with epsilon tensor. So by rewriting the equation motion in this way, so you can see that this theory describes the massive degree of freedom. So then Chern-Simons term behaves as a topological mass term for the gauge boson. Okay. So first of all, 3D gauge boson, which has a single degree of freedom, so then which is dual to a real scalar. So the naive 3D Seiberg duality includes additional flat direction. So if you consider naive dimensional reduction of the 4D Seiberg duality, such as 3D Seiberg duality includes additional flat direction from the gauge boson. So therefore, so in general, 4D Seiberg duality cannot hold in 3 dimensions because we have additional flat direction from the gauge boson. And this additional flat direction cannot match under the 3D duality. So we need some modification to have a correct 3D Seiberg duality or Seiberg-like duality. So however, in Chern-Simons theory, so gauge bosons are massive because Chern-Simons term behaves as a mass term for gauge boson. And it might be possible that the 3D duality, very similar 3D duality can hold. So actually, Gibeon-Kutasov duality is one of the such examples. So Gibeon-Kutasov duality claims that following two theories are completely identical in the finite limit. The electric theory is a 3D n equal to 2 UN gauge theory. And here K is the Chern-Simons level. And this theory has 4 supercharges. And the electric theory is a UNK gauge theory with F flavor. Here F flavor again means the F fundamental chiral multiplet Q and the F anti-fundamental chiral multiplet Q tilde. So this is nothing but a supersymmetric QCD plus Chern-Simons term. And please note that, so in this gauge group, so UN fundamental means this type of Young tableau and UN anti-fundamental means this Young tableau. Okay. And this theory is dual to a 3D n equal to 2 U F plus K minus N Chern-Simons gauge theory. with Chern-Simons level is minus k. And the matter contents consist of F dual flavors and the Meson singlet. This matter content is completely the same as usual for the magnetic dual. So F dual flavor is F fundamental chiral multiplet Q and F anti-fundamental chiral multiplet Q chilled. And this theory has a Yukawa type superpotential, MQQ chilled. Okay. So today, I would like to generalize this Gibeon-Kutasov duality. So by the way, so for a unitary gauge group, we can introduce two types of Chern-Simons terms. So we can introduce the Chern-Simons term for non-abelian part, SUN part, and you can introduce another Chern-Simons term for abelian part. So for example, we can introduce the usual Chern-Simons term by using the UN gauge field like this. This is a usual Chern-Simons action for the non-abelian gauge group. And we can also introduce the Chern-Simons term for the trace part of this gauge field, because now we are considering the UN gauge group. So this is not traceless, so then you can introduce a Chern-Simons term for the trace part. So then in total, you can introduce two integers, k and small n. And today, I will write this theory as a UN k comma k plus nn Chern-Simons gauge theory. The first k means denotes non-abelian SUN Chern-Simons term, because SUN Chern-Simons term is coming from this usual Chern-Simons term. And k plus nn is a Chern-Simons term for the U1 subgroup. This is because so U1 Chern-Simons term is coming from this usual Chern-Simons term and also from this trace part. So then U1 Chern-Simons term becomes like this, k plus nn. Okay. Okay, let me briefly explain the motivation of generalizing Chern-Simons terms. So first of all, because this is a generalization, so then we want to consider this type of generalization because we don't know what happened for when generalizing this Chern-Simons term in this way. So we don't understand the low energy dynamics of this type of generalized Chern-Simons gauge theory. So then it's nice to understand the physics of this generalized Chern-Simons levels. And even for a non-generalized normal Chern-Simons theory, its dual is sometimes given by a generalized one. And the generalized UN Chern-Simons gauge theory is more ubiquitous than expected. And recently, non-supersymmetric 3D bosonization was very much studied. And this is a spin transmutation by using Chern-Simons interaction. Due to Chern-Simons interaction, bosonic particle is transmuted to fermion, or fermion is transmuted to a boson due to the Chern-Simons interaction. So in this 3D bosonization, we are introducing generalized Chern-Simons term. So then it's nice to understand the effect of this generalized Chern-Simons level. Okay, let me give you more explanation for the second part and the third part.
I have one question about this
please.
fourth word. So
Sorry,
here, the fourth word, so recent, you mentioned a non-3D bosonization. Can you explain a bit more? Or whose work is this?
So recent working of Seiberg and his collaborators are working on this type of 3D bosonization 2 or 3 years ago.
Oh, okay. Okay. So there is some spin boson, sorry, fermion boson like a duality in 3D.
Yeah.
Using Chern-Simons interaction.
Yeah.
Oh, okay.
So Chern-Simons theory is a topological theory, but this interaction changes the spin of the particle.
Okay.
So Chern-Simons, for example, complex scalar coupled Chern-Simons action is normally called the anion system, right?
Yeah.
So
yeah,
anion
yeah.
has a non-integer spin.
Oh, I see. Okay.
So recent proposal of the 3D Bostonization is using generalized Chern-Simons interaction.
Okay. Thanks.
Okay. Okay, let us consider the following example, so which is 3D n equal to chiral SUN Chern-Simons gauge theory. So this theory is chiral, so this theory has F quarks and F bar anti-quarks. This is not a vector-like theory. So in 4 dimension, there is a chiral anomaly for the gauge group, so we cannot consider this type of theory, but in 3 dimension, this theory is well defined. And the electric theory is a super 3D n equal to SUN Chern-Simons gauge theory, whose level is Chern-Simons level is K. And this Chern-Simons level satisfies the following condition. So in this case, its dual is given by UN tilde Chern-Simons gauge theory with level minus K comma minus K plus N tilde. Yeah, N tilde is given by this. So in this way, the dual side becomes a generalized Chern-Simons gauge theory, even for a usual SUNK Chern-Simons gauge theory. So in addition, we know a lot of 4D duality, which includes SUN gauge groups. For example, as I already explained, the convention of the SUN Seiberg duality is based on the SUN gauge group. And you can introduce additional matter in various representation. So in that case, dual is also given by in some unitary gauge theory. And if we consider the spin n gauge theory, its dual is given by SUN gauge group. And if we consider the J2 supersymmetric gauge theory, its dual is given by SUK gauge theory. So when we consider the 3D version or 3D Chern-Simons version of this 4D duality, so we need to take into account some generalized UN Chern-Simons interaction. So then it's very nice to study the dynamics of the generalized Chern-Simons gauge theory. Okay, this is the motivation of my study. Okay, purpose of this paper is to study the low energy dynamics of the generalized UN K comma K plus NN Chern-Simons gauge theory and to discuss the duality as a byproduct. Okay, this is the motivation. Okay, here is the plan of my talk. So first, I will briefly review the 3D gauge theories and 3D supersymmetry. And after that, I will introduce a generalized Giveon-Kutasov duality. And as a check of this duality, I will show you some analysis of the Coulomb branch. And finally, as an application of this duality, I will show you some application of this duality. Okay. So is there any question so far?
I have one question. So in 3D experiment does not produce chiral anomaly.
Yeah.
Okay, it's because there is only single chirality. Is there no chirality in 3D?
No chirality.
I see. Okay. And what is the parity anomaly?
So parity anomaly is so how to say? So for example, if we consider some, for example, SUN gauge theory with only one chiral superfield. So such a theory has a parity anomaly.
I see.
So then that theory is not well defined in 3 dimension. In order to have a well-defined theory, we should introduce a Chern-Simons level with a half-level Chern-Simons level.
I see. That's okay. That counts on parity anomaly.
Yeah.
Okay. And you also mentioned about the confinement versus number of supersymmetry in the beginning. So to have confinement, why do you need you cannot have so many supersymmetries.
Yeah, that statement was very sloppy. So actually, in 3 dimensions, we have a confinement phase for n equal to 4. For system with 8 supercharges. But in general, we cannot have confinement phases for the system with 8 supercharges. This is because, for example, in 4 dimension with 8 supercharges, so the theory should have a Coulomb phase. So then, yeah, confinement phase is impossible. So we always have a Coulomb phase. Coulomb phase is not a confinement phase in 4 dimension.
Okay, so you mean so in Seiberg-Witten theory for 3D n equal 2, the gauge group broke into U1 at the generic point of Coulomb branch, and you get the Coulomb phase, you mean?
Yeah. But in 3 dimension, Coulomb phase is very similar to confinement phase because U1 photon is dual to a scalar.
Oh, I see.
So then confinement phase is possible in 3
dimension. Okay. And here you don't consider adjoint matter. You only consider fundamental. Okay.
Fundamental matter or anti-fundamental matter.
Okay. Thank you very much.
Yeah. Okay, let me start with a brief review of the 3D gauge theory or 3D supersymmetric gauge theory.
Sorry, I have a question. So, is this parity anomaly a special case of global anomaly?
Parity anomaly. So, parity anomaly is related to the quantization of the Chern-Simons level. So for example, if you consider some SUN gauge theory with only a single chiral multiplet, so in that case, if you integrate out this chiral multiplet, you will get the half-level Chern-Simons level. It's not a well-defined quantum theory, right? Chern-Simons level must be integer. However, if you consider such a SUN gauge theory with a single chiral multiplet, such a theory leads to a ill-defined Chern-Simons theory. So such a theory is not well defined. This is called a parity anomaly.
Okay, thanks.
Okay, so let me first explain some dynamics of the 3D U1 gauge theory. So first of all, so 3D gauge coupling is dimensionful, which has a mass dimension. So then 3D gauge interaction is a super renormalizable. So then by defining a dimensionless coupling in this way, G square divided by energy, and if you consider the low energy limit of this theory, this gauge coupling becomes strong in the infrared. So this means that even U1 interaction is very strong in the infrared. So the difference between SUN and UN is very important. And the second property is a 3D photon, which has a single degree of freedom. It's dual to a scalar field. So you can define a scalar field in this way. So by using the field strength, you can define a real scalar. And this A, real scalar A, is called the dual photon. So 3D photon is dual to a real scalar. And today, I'm going to consider the 3D n equal to 2 supersymmetric gauge theory, which has 4 supercharges. This theory can be obtained by dimensional reduction from the 4D n equal to 1. 4D n equal to 1 also has 4 supercharges. And we are interested in low energy dynamics of this theory. So we have to understand the flat direction of the scalar potential. So in this theory, there are 2 types of flat directions. So first one is called Higgs branch. So Higgs branch is a flat direction from the chiral superfield. So chiral superfield can be expanded in this way. So first component is a complex scalar, and this complex scalar spans a flat direction. And today I will call this flat direction Higgs branch. And another flat direction is called Coulomb branch. And the Coulomb branch is a flat direction from the vector superfield. So in 4 dimension, vector superfield can be expanded in this way. So gauge field and gaugino field. So there is no scalar field. However, in 3 dimension, this can be dimension reduced to 3D. And this first component is 3 directions of the gauge field. And the third direction of the gauge field is identified with a scalar phi. And by dualizing this 3D gauge field into a dual photon, so we have 2 real scalars. So then by combining the 2 real scalars into a 1 complex scalar, so vector multiplet, vector superfield has a 1 complex scalar field, V. Okay. So in this way, complex scalars are coming from the vector multiplet in 3 dimensions. So for non-abelian gauge groups, this scalar becomes adjoint. So the most important point is that the Coulomb branch gets large quantum correction. So this is the most difficult point of the surge gauge theory. So, okay, let me start with the classical picture of the Coulomb moduli space. Okay, so first of all, Coulomb moduli space is a flat direction of the adjoint scalar in the vector multiplet. This is the definition of the Coulomb branch. And since now the gauge group is broken by the adjoint wave. So yeah, this flat direction is parameterized by this adjoint scalar. So then gauge group is spontaneously broken by this adjoint wave. So then rank is not reduced. So then along the classical Coulomb branch, for example, we can have the following symmetry breaking patterns. For example, if we consider the UN gauge symmetry, UN gauge group is broken to U1 cross UN minus 1 and U2 cross UN minus 2, or you can also consider UA cross UN minus A minus B times UV, something like that. So you can consider various breaking patterns. And all breaking and which correspond to each direction of the Coulomb branch is classically allowed, but quantum mechanically, almost all the directions are eliminated from the moduli space. And in addition, today I'm going to consider Chern-Simons gauge theory, and Chern-Simons term is a mass term. So then naively, it looks that there is no Coulomb moduli space for the Chern-Simons theory, because gauge bosons or vector multiplets are becoming massive due to the Chern-Simons term. So it looks that there is no Coulomb moduli space for Chern-Simons theory. Okay, let me first explain some quantum effect of the Coulomb branch. Okay, as an example, let us consider the UN supersymmetric UNS gauge theory with F flavor. And let us consider the following Coulomb branch. So UN is broken to U2 cross UN minus 2 along the Coulomb branch. So this breaking is associated with the following vacuum expectation value. So adjoint scalar takes the following non-zero waves. So there are 2 non-zero entries and all the other components are 0. So due to this vacuum expectation value, the gauge group is broken like this. And the matter fields are decomposed like this. Okay, since we have a Yukawa interaction between fermions and this adjoint scalar, so these components surrounded by this pink circle are massive along the Coulomb branch. So as a result, the low energy limit of this U2 part includes a pure supersymmetric SU2 gauge theory, because these matter are massive along the Coulomb branch. So we have a pure SU2 super-Yamil theory. And in this theory, monopole generates some potential and making its vacuum run away. And monopole creates some repulsive interaction between these two vacuum, two eigenvalues. And in addition, we can compute the Witten index of this pure SU2 super-Yamil theory, and this whose Witten index is 0. So this means that means that there is no supersymmetric vacuum. So as a result, so because this monopole generates some repulsive force between these eigenvalues, so as a result, the quantum mechanically allowed Coulomb branch is like this. Only one entry is non-zero, and all the other entries are zero. And this wave corresponds to the following breaking. So UN is broken to U1 cross UN minus 1. Only this Coulomb branch is quantum mechanically allowed.
I have one question. So
Yeah.
what is U1 part of U2 went? Because I mean you said you have pure SU2 super mLs.
Yeah. But
low...
yeah, I think U1 part is in this case has no interesting phenomena because U1 part has no matter, so U1 photon is completely free and decoupled from the SU2 part. So of course you can consider U2 gauge theory directly. But yeah, now U1 sector is completely decoupled from the SU2 sector.
Okay.
And in today's talk, so I will consider the supersymmetric Chern-Simons gauge theory, which is a massive theory. And today I want to claim that even in Chern-Simons theory, the Coulomb branch remains massless, and the test of the duality becomes very non-trivial. Okay, in order to understand the quantum structure of the Coulomb branch in Chern-Simons gauge theory, I have to introduce two properties of the 3D gauge theory. Okay, so first property is about topological U1 symmetry. So when the theory has U1 gauge symmetry, we can define a conserved current. So by contracting the indices of the field strength with epsilon tensor, you can define a conserved current F tilde mu. So this current is topologically conserved. And if we consider the associated charge of this current, this charge is proportional to a time derivative of dual photon. So this is nothing but momentum of the dual photon. So then this generator corresponds to a shift of the dual photon. So this charge generates a shift of this dual photon like this. So if we remember that the Coulomb branch has the following dependence of on the dual photon like this. So this Coulomb branch coordinate has a non-zero topological charge. And the second property is about some consequence of the Chern-Simons interaction. So first of all, Chern-Simons term is a topological mass term. So if you consider the Maxwell Chern-Simons theory and if you write down its equation motion in terms of this topological current, you can see that this gauge boson has a mass term. And another property is about a mixed Chern-Simons term. Okay, suppose there are two U1 gauge symmetry, A1 and A2. And suppose this matter sector is charged under the second U1 gauge symmetry. So A2 coupled to this matter sector, matter current. Okay, let us consider this type of setup, and let us consider some Gauss law constraint of this. And the Gauss law constraint says this topological current associated with this first U1 gauge symmetry should be proportional to this matter current. So this means that a topologically charged object, for example, Coulomb branch operator is also topologically charged. And this topologically charged object also has matter charges. So this property has a very important effect on the following discussion. Okay, so first of all, Coulomb branch coordinate parameterize the flat direction of the adjoint scalar in the vector multiplet. So the Coulomb branch coordinate are neutral under the flavor symmetry, which rotate the chiral multiplet. This is because Coulomb branch coordinate are defined from the vector multiplet. So Coulomb branch coordinate can be defined from the component of the vector multiplet. So it's neutral under the matter symmetry. However, due to this mixed Chern-Simons, the Coulomb branch coordinate becomes charged under the matter symmetry. So this is the most important point of understanding the Coulomb branch structure. Okay, by keeping this in mind, okay, let me propose a generalized Giveon-Kutasov duality. So generalized Giveon-Kutasov duality is like this. So the electric theory is a UN Chern-Simons gauge theory, whose Chern-Simons level is k comma k plus nn. So first k is a Chern-Simons term for the SUN part, and k plus nn is a Chern-Simons term for the abelian part. And the matter contents is consists of F flavors. F flavor again means the F fundamental chiral multiplet Q and F anti-fundamental chiral multiplet Q children. So this is the SQCD plus generalized Chern-Simons term. And the dual description becomes a bit complicated, but the dual magnetic theory is a U1 cross F, UF plus K minus N Chern-Simons gauge theory. And the Chern-Simons level of the first U1 subgroup is N plus 1. And the Chern-Simons levels of the non-abelian part is minus K comma F minus N. And there is also a mixed Chern-Simons term between these two abelian subgroups with level 1. And this first U1 gauge symmetry is a gauged topological U1 symmetry associated with overall U1 part of the UF plus K minus N. So we have a U1 symmetry, so then we have an associated topological U1 symmetry and we can gauge it. And this U1 symmetry corresponds to it. And the matter contents on the dual side is completely the same as usual Seiberg duality. So this consists of F dual flavor, F fundamental chiral multiplet small q, and F anti-fundamental chiral multiplet q children, and a meson gauge singlet, M. So we also have a Yukawa type superpotential, MQQ children. Okay, first I will explain that this duality is consistent with the usual Giveon-Kutasov duality for n equal to 0. So by taking n equal to 0, so on the electric side, so this electric theory reduces to usual Giveon-Kutasov duality. Okay, so we should check that whether this right-hand side goes back to the original Giveon-Kutasov one. Okay. So when n equal to 0, we can pass integrate the U1 vector multiplet. Okay, let us remember that the magnetic gauge group is like this. And by defining the new gauge field, so by taking a linear combination of the two U1 gauge field in this way, so this gauge group is recast into the following form. So U1 new cross UF plus K minus N. And the Chern-Simons levels are mapped in this way. So importantly, there is no mixed Chern-Simons term between these two U1 there is no mixed Chern-Simons terms between these U1 field, U1 gauge field. And since dual quarks are neutral under the new U1 gauge symmetry, the U1 vector multiplet can be integrated out. So notice that due to the quantization of the Chern-Simons term, we can do this type of we can take this linear combination only for the case as Chern-Simons level equal to plus minus 1. So by integrating out this U1 new gauge field, we obtain the following duality. So electric side is a UN k comma k supersymmetric Chern-Simons matter gauge theory with F flavor. So in the literature, this gauge theory is written simply as UNK. And its dual is given by UF plus K minus N Chern-Simons gauge theory, whose level is minus K. So in this way, we can obtain the usual Giveon-Kutasov duality. Okay. So as another test of this duality, let us consider the small n to infinity limit. So for small n equal to infinity limit, we can also obtain a non-duality. So in this limit, we can forget about the U1 Chern-Simons gauge field interaction. So because very roughly speaking, Chern-Simons interaction, strength of the Chern-Simons interaction is given by 1 over k, 1 over Chern-Simons level. So then by taking n, small n to infinity limit, we can forget about the U1 Chern-Simons interaction. So then simply UN k comma k plus n gauge theory is reduced to the SUNK Chern-Simons gauge theory is F level. Okay. And on the magnetic side, this limit, by taking this limit, we can forget about the dynamics of the first U1 gauge theory. So we can drop this first U1 gauge dynamics, and we will get UF plus K minus N Chern-Simons gauge theory, whose level is minus K and F minus N. And this duality was, for example, known in the literature, for example, in this paper. Okay. And as a final test of this duality, okay, let us consider the generalized Giveon-Kutasov duality for n equal to -1. So in this case, the electric side is a UN Chern-Simons gauge theory, whose level is K and K minus N. And on the magnetic side is like this. And the matching of the Higgs branch is very straightforward because the matter sector is completely the same as usual Giveon-Kutasov duality or usual Seiberg duality. And because the gauge group is now unitary, not special unitary, there is no baryonic operator. So then we should only check the meson matching. And the meson matching is completely the same as for D1. So QQ tilde is identified with M. So however, the matching of the Coulomb branch is very non-trivial. Since we have Chern-Simons terms, it looks that there is no Coulomb moduli space in this theory. Okay, let us see this matching in more detail. Okay, let me start with the analysis of the electric Coulomb branch for n equal to -1. And the Coulomb branch is a flat direction spanned by the adjoint scalar in the vector multiplet. And now I will consider the following Coulomb branch. UN gauge group is spontaneously broken to UC times UP. And this breaking is generated by the following adjoint wave. So there are C non-zero entries and all the other components are zero. So due to this vacuum expectation value, the gauge group is broken like this. And the matter fields are decomposed in this way. Okay. And the bare Chern-Simons levels are decomposed as follows. And you can see that, first of all, so this adjoint wave corresponds to the U1 generator of the UC in the UC subgroup. And you can, from this Chern-Simons levels, you can see that the Coulomb branch is generally massive because Chern-Simons level for the U1 C part is K minus C. So this vector multiplet is associated with this U1 generator is massive, except for C equal to K. For C equal to K, this U1 C vector multiplet becomes massless. So I claim that this theory has a flat direction from the Coulomb, from the vector multiplet. So this flat direction is parameterized by this C equal to K. And I would like to claim that this flat direction, even non-perturbatively stable. Okay, let us consider this breaking. So along this breaking, so these components are massive. These components circled by this pink line are massive. due to Yukawa interaction. So then this UC part becomes a pure SUK Chern-Simons supersymmetric Chern-Simons gauge theory, whose Chern-Simons level is K. And we can compute the Witten index of this pure SUK Chern-Simons gauge theory. And we can show that Witten index is unity and lead to a supersymmetric vacuum. So then this breaking pattern is non-perturbatively stable. So, okay, so in this way, this flat direction is non-perturbatively stable and exactly massless. However, due to the mixed Chern-Simons between U1C and U1P, so U1C is the overall U1 factor of the UC subgroup, and U1P is the overall U1 factor of the UP subgroup. And there is a mixed Chern-Simons. So due to this mixed Chern-Simons, via Coulomb branch coordinate have a non-zero U1P charge. So this Coulomb branch coordinate is not gauge invariant, and we cannot use this as a coordinate of the moduli space. So then we need to introduce, or we need to define a gauge invariant composite by using this via coordinate. So now you can see that this component surrounded by green line is massless. So by using this component, we can define a gauge invariant composite. So Coulomb branch is dressed by this baryonic operator. And so in this way, we can define two types of gauge invariant composite from vector multiplet and chiral multiplet. So this operator describes a mix of branch, which consists of Coulomb branch and Higgs branch. Okay. Okay. Next, let us see the same flat direction from the magnetic side. Okay, on the magnetic side, the gauge group becomes like this. And here I will take n equal to -1. So for n equal to -1, you can see that this Chern-Simons term of the first U1 subgroup is exactly 0. So then U1 vector multiplet becomes massless, and you can introduce a Coulomb branch coordinate. So however, there is a mixed Chern-Simons term between these two U1 Chern-Simons factors, between the two U1 Chern-Simons fields. So then this bare coordinate, U plus minus, has a non-zero U1 charge. So then we have to define some gauge invariant coordinate to describe a Coulomb moduli space. So now you can see that this combination becomes exactly gauge invariant. And today I will not explain the computation of the other quantum numbers of this operator, but by computing the quantum number of this composite, so you can see a natural identification between these two composites. So in this way, we can find a nice agreement of the Coulomb branch. So more correctly, a mixed branch. Okay, so is there any question so far?
Okay, I have a question.
Yeah.
So when you write this U plus a minus, it's a plus minus, it's a U1 charges.
Yeah, rigorously speaking, so now I'm defining the Coulomb branch in, for example, like this. So
yeah,
so
this
positive phi has a positive phi has a positive topological U1 symmetry, and negative phi region has a negative topological charge. So then, yeah, this was a bit sloppy, but you should distinguish V plus and V minus. So,
and how does this in a mixed branch? How do you show this the Q3 some power has opposite topological charges?
Yeah, no, this has a topological charge. So V minus has negative topological charge, -1.
Okay.
And this composite has a plus.
Sorry. So okay. Q, capital Q or small q, do they have topological charges? Sorry.
No, this U plus has topological charge and this U minus has topological charge.
Yeah, but Q doesn't, right?
Yeah, Q, no.
Oh, okay,
This
okay,
is
okay.
a matter field.
Okay, okay. So, okay, this composite one, oh, okay, so I see, I understand. So the gauge singular means that the, under which gauge group? U F plus K minus N or UK?
More correctly, no. Yeah, under this gauge group.
Oh, okay, okay, I see.
So more rigorously speaking, this UF plus K minus N gauge group has topological U1 symmetry, and this topological symmetry is gauged, and this that corresponds to this. And this is gauged, so then you can define, you have additional topological U1 symmetry.
Okay.
So, and this U plus minus are charged under this topological, new topological symmetry.
Oh,
and this P plus minus is also topologically charged under the topological symmetry of this.
Okay, okay, thank you.
Okay, so finally, I will show you some application of this generalized Giveon-Kutasov duality. So, okay, let us consider the abelian case. So in case of an abelian gauge group, the duality becomes very special. Okay, let us take capital N equal to 1 limit. So this becomes U1 to, whose Chern-Simons level is K plus N. And on the electric side, always, so K plus N appears, K and N appears always in this combination. So then by defining the K tilde in this way, so electric side is parameterized by K tilde. However, on the magnetic side, so please remember that the magnetic gauge group, which is like this, and K and N independently appear. So by keeping K tilde fixed, and by changing K and N independent, by changing K and N, so there are infinite number of magnetic duals. Okay. So 3D n equal to 2 supersymmetric U1 gauge theory has an infinite number of magnetic duals. So especially in this talk, I will consider the very special limit K tilde equal to 0. So this is nothing but the SQED limit. So for n equal to minus K, so this corresponds to the SQED limit. And we know there are two known dualities. So the electric theory is a U1 supersymmetric QED with F flavor. This theory has no Chern-Simons term. And we know two dualities. So one is known as a Haroni duality. And this is a usual 3D version of the Seiberg duality. And its dual is given by UF minus 1 supersymmetric gauge theory. Its Chern-Simons level is 0. And we also know the mirror symmetry. And mirror dual is given by U1 to the F divided by U1 gauge theory. And now, by using the generalized Giveon-Kutasov duality, we can have a Chern-Simons type duality, which is given by this gauge group. And by changing the K, by changing the value of K, you can have infinite number of magnetic duals. Okay. Okay, let me consider.
I have one question. Can you go back one second? So this Haroni duality doesn't have any matter.
Yeah, this theory has usual matter contents. Yeah, very similar to usual Seiberg duality. So,
I see.
Yeah, but for simplicity, I'm omitting
you just omit it.
the matter content. Yeah.
Okay.
Okay, let me consider the, okay, let us consider this theory in more detail. The electric theory is a 3D n equal to 2 supersymmetric U1 gauge theory with F electrons and F positrons. And its Chern-Simons level is 0. And since Chern-Simons term is absent, so Coulomb branch can exist. And the classical picture of the Coulomb branch is as follows. So vector multiplet has a real scalar phi, and the gauge field is dualized to a dual photon A. So by combining these two real scalar into one complex field, so the classical picture of the Coulomb branch is like this. So it's a cylinder. So A is a compact variable and phi is non-compact. So this moduli space is like a cylinder. And however, the quantum picture of the Coulomb branch is drastically changed. So one loop correction modifies the metric of the moduli space. And this correction pinch this cylinder in this way. So then we need to introduce two coordinates. So for positive phi region, we introduce V plus field. And for negative phi region, we introduce V minus field. So in this way, one loop correction modified the quantum picture of the Coulomb branch. Okay, we can see this effect from the magnetic side. Okay, on the dual side, the dual gauge group was like this. So since Chern-Simons terms are turned on for all the gauge group, all the U1 part and semi-simple subgroup. So then almost all the Coulomb branches are massive. However, we can see that when two adjoint scalars of these two vector multiplets obtain non-zero vacuum expectation values, the corresponding U1 direction becomes massless. So let us introduce the following vacuum expectation value. For the U1 adjoint scalar, we introduce wave V, and for the non-abelian part, we introduce the following vacuum expectation value. There are k-1 non-zero entries, and all the other components are zero. And this vacuum expectation value breaks the gauge group as follows. So U1 part is not broken. However, this non-abelian part is broken like this. And the linear combination of the first two U1 gauge field becomes exactly massless. And depending on the sign of V, so there are two Coulomb branch coordinates. So U plus and U minus describe the Coulomb branch associated with the first U1 subgroup. And V plus and V minus describe the Coulomb branch associated with the U1 subgroup of the UK minus 1. And almost all the Chern-Simons terms vanish along this flat direction, U plus V plus, except for a mixed Chern-Simons term. So due to this mixed Chern-Simons term, these coordinates, U plus V plus or U minus V minus, obtain U1 charges under the U1 subgroup of the UF gauge group. So in order to describe the moduli space, we need to construct some gauge invariant composite. So now, in this breaking, the matter fields are decomposed as like this. So, and these components are massive due to the Yukawa interaction. However, these last components are massless, and these components are charged under the U1 symmetry. So then by using these components, we can define a gauge invariant composite in this way. And from these quantum numbers, we can identify this with V plus and V minus. So in this way, we can check the matching of the Coulomb branch. Okay, let me summarize. So in this talk, I studied the low energy dynamics of the 3D n equal to 2 supersymmetric UN Chern-Simons matter gauge theory by generalizing the Chern-Simons levels. And I analyzed the quantum structure of the Coulomb branch and proposed the duality. So although today I didn't explain, but I found some confinement phases of the generalized Chern-Simons gauge theory. So about confinement phase, you can easily find. So from the dual gauge group, confinement phase, roughly speaking, confinement phase appears when the dual gauge group becomes null. So then F plus K minus N becomes 0. So in that case, the theory shows confinement phase. And for U1 cases, there are infinite number of Chern-Simons type Seiberg duality. And as a future problem, I hope that we can consider spin or G2 Chern-Simons gauge theory. And these theories require some generalized Chern-Simons gauge theory. And as a future direction, I hope that we can derive some spin or G2 level rank duality. Okay, I will stop here. Thank you very much.
Thank you very much. Other questions from audience?
I have a question. So, in this three-dimensional supersymmetric Chern-Simons theory, there are many loop operators like BPS with loops and vortex loops. Have you considered how these loops map to each other under these new dualities?
Sorry, I can't hear you. So say again. So his question is: have you ever considered some BBS line operator in the 3D N-equal-2 theory? No, I haven't. So yeah, it's possible to consider some Wilson loop or some loop quantity. But I computed the superconformal indices, which is counting the BPS half BPS operator or half BPS state. So yeah, we can match the half BPS state local operator. I have checked the only local operator, not the non-local one.
Okay, thanks. And
Yeah, thank you very much.
Also, thanks, Satoshi. Okay, thanks.
No problem. Have you ever considered 2D limit? What's going to happen? 2D limit is very complicated. So, yeah, for example, Aharoni already considered the dimensional reduction of the 3D duality to 2D, but in 2 dimension, we shouldn't talk about modular space because we should talk about the target space, because in 2 dimension, we cannot have a spontaneously symmetry breaking, right? So we have a no-go theorem for the spontaneous symmetry breaking in 2 dimension. It's not allowed. So for example, in modular space picture, if we introduce some vacuum expectation value, it is nothing but a symmetry breaking. Because these modular space coordinate has some global charges, and this corresponds to some spontaneous symmetry breaking. But in 2 dimension symmetry breaking, spontaneous symmetry breaking is not allowed, and we should consider target space. So in 3 dimension, modular, we can consider very particular point of the modular space, and we can consider very tiny fluctuation around that point. So however, in 2 dimension, we should consider the entire space of the target space. And so this is very complicated. You mean target space means you need to consider sigma model? Yeah. I see. To the modular space. Yeah. Okay. And in that case, check of the duality becomes very complicated, and naive dimensional reduction does not work. So however, so on the magnet, so for example, in some case, the magnetic gauge group becomes null. For example, F plus K minus N is 0. So in this case, theory shows the confinement phase. In that case, I hope that dimensional reduction is becoming more easier than other cases. But how does Chern-Simons term behave under the dimensional reduction? So on this side, it's okay. So yeah. Does it become some kind of twisted mass or something in 2D? No, just speaking loud. Maybe audience, some audience know. So sorry, I don't remember the reduction of this theory to 2D. Okay. Yeah, but I think it's possible for the confinement case. Okay. It's easier. Okay. Any other question from audience? Okay, if not, let's thank the speaker again. Thank you very much. And I will leave the space for some informal discussion. So if you want to ask him more detail, just stay here. So thank you very much. So you said when you consider U1 gauge theory, there are infinite many dual by changing Chern-Simons level.
Yeah.
But does it become so at the level of superconfirmation index? How does the identity look like as a superconfirmation index? So for instance, U1 with two flavors, the simplest case.
Yeah.
Then how does the identity look like?
Two flavor case.
Then it becomes,
So you are talking about superconfirmation indices or?
yes, superconfirmation index. How does I mean it becomes an identity, right?
Yeah.
But there are infinite many identity. How does it? What does it mean as some special function or something?
I'm not sure, but just I'm expanding the superconfirmation
okay.
indices, and I observe the exact matching.
Okay.
But yeah, I don't study the identity. But this duality is very confusing because on the electric side, so this SQED limit corresponds. So there is no Chern-Simons term. So this side has a time reversal symmetry. So, but on this Chern-Simons side has various Chern-Simons interaction. This is not parity invariant. So in this description, parity invariance is an emergent symmetry. So then this duality is a bit confusing compared to other two.
I see. I see. Let's see. So you can also add, if you add adjoint, there's duality called Kutasov-Schwimmer duality.
Yeah. In 3 dimension, it's known. And recently, yeah, I think it's possible to generalize the given Kutasov-Schwimmer duality for this type of generalized one.
Oh, I see.
But I didn't check the.
Okay, I see. So, but there is also 4D version of Kutasov-Schwimmer, right?
Yeah.
Yeah, you include the adjoint.
Yeah.
I see. How about the 2D 0,2 version?
Okay. So for example, 0,2 or in 3D case, it's a 3D n equal to 1.
Yeah.
So in that case, it's very difficult to derive the generic duality, but it's possible to derive a duality when the magnetic side becomes null. So if the theory shows confinement phase, the dual description becomes the usual Bess-Zumino model. So in that case, it's easy to derive a duality. So you can consider 3D n equal to 1 or 2D 0,2. So now probably up to my knowledge, so yeah, for confinement case, we can derive some duality.
Why the confinement case, the dimensional reduction is easy?
The Bess-Zumino side is straightforward. There is no ambiguity.
I see. What do you mean ambiguity?
Yeah, so so for example, in 2D limit, so yeah, this 3D theory or 4D usual Seiberg theory, Seiberg duality has non-compact moduli space. And if we have a non-compact moduli space, the reduction becomes very complicated.
I see.
Because we should consider target space, entire space of the moduli space.
I see. I understand what you mean. Okay. I see. But 2D 0,2 you can compute elliptic genus.
Yeah, I think so.
Whereas 3D n equal to 1, you cannot compute partition function, can you?
It's impossible. 3D n equal to 1, we cannot.
I see. Huh. Interesting. And do you have some brain construction for these dualities?
I have no idea for this generalized Chern-Simons gauge theory because in brain setup, I don't know how to realize this generalized Chern-Simons.
I see. I see. Interesting.
Yeah, but of course we have a brain construction of this U1 gauge theory. So this is just a SQ, it's supersymmetric.
Yeah. Oh, but I see. You don't know how to realize. Okay. This mixed Chern-Simons and so on.
Yeah. And the generalized Chern-Simons term is also difficult.
I see. Then in the middle of the talk, you said monopole generates the potential.
Yeah.
But how does it work?
Very roughly speaking, so. Okay. So in general, we can consider some vacuum expectation value of the adjoint scalar phi 1, phi 2, phi 3, phi 4, phi 5, blah. And monopole, very roughly speaking, monopole generates some repulsive force. So for example, how to say? Yeah. How to say? So monopole generates some potential 1 over exponential phi 1 minus phi 2, something like this. So then we should take a very, we should separate phi 1 and phi 2.
Oh, I see.
So monopole always generates such kind of potential. So then pure SU theory or pure SUN gauge theory is always unstable.
I see.
It has a runaway potential.
I see. And you also talk about decomposition Chern-Simons level.
Yeah.
That part I didn't understand how it works also. How does? Yeah, this one.
Yeah, this is just a brute force calculation. Just I'm decomposing this UN gauge field in terms of this UC gauge field and the UP gauge field.
And then just write down the action or Lagrangian.
Yeah.
In terms of that, okay.
Yeah.
I see. Okay, and then with this configuration, the gauge group becomes UC. You mean?
Yeah. This is also this is very sloppy. So very strictly speaking, this should be how to say? Yeah, UC times UP. How to write down this breaking? So.
UC.
How to write UC UP.
No, what I meant is it seems like you ignore U or P part.
Yeah. Because now I'm introducing the wave in this way. So I'm focusing on the Coulomb branch of the UC part.
Okay, I see.
And this breaking pattern is also incorrect. I'm omitting the global structure.
What do you mean global structure?
Yeah, because I think this is maybe this is correct.
Oh,